Now, of course, all these games are guaranteed to have Nash equilibria because you just take the last profile in this finite path. That's going to be a Nash equilibrium. So I'll just define what is this congestion game. So congestion games are defined as follows. So you have a set of players 1 to n. You have a set of facilities or resources. Let's call it. So this is a finite set R. Okay. Think one nice way of thinking about this is suppose you have a road network. So everyone wants to go from, let's say, point A to point B. There are these road segments which connect A and B. So the set of road segments is going to be the set of resources. Now to reach from A to B, you have to pick some subset of resources, right? And then travel on that subset. That's how you reach from A to B. So the strategy set for each player is simply the power set of R. So each player can choose a subset of resources. Okay, so that's the strategy. Now, each facility J or each road segment J has a delay function dj associated with it. And what is this function? This function is from the set 1 to n, there are n players, the set 1 to n to the set of real numbers. So what does it essentially tell you? Well, dj of k, so j is a resource, k is some number between 1 to n. This tells you the delay on using this resource j when there are k other people using the resource j. In total, if there are k people using the resource. Okay. Now, what is the cost? So now if you fix a strategy profile, remember each strategy is a subset of resource. So strategy profile is an n tuple where each component is a subset of resource. Okay. Now if you fix a strategy profile, then what is the cost? So what is the cost that player I has to incur on the strategy profile? You simply add up the delays. Right? You look at all the resources that are part of that strategy of player I, you simply add up the delays. Okay, so that's the cost. So this is the congestion game model. So here you are trying to minimize the cost. If you want to think of it as utility, you just take the negative of this value, then you are trying to maximize the utility. Okay. Now the theorem is that every congestion game is a potential game. So this I already mentioned yesterday. So this is also an example of a game where the potential function is not the social welfare function. That doesn't work. So it's essentially some kind of a discrete integral. Okay, so it's not very difficult to show that it's actually a potential game, but I said that you can also show the converse. Every game which has a potential, every potential game is actually a congestion game in some disguise. So you can rewrite it in a particular way such that you get back a congestion game. Okay. Okay. So this is what we were discussing yesterday. So what I want to talk about today is look at a subclass of strategic form games and ask the same kind of questions that we were discussing yesterday. So Nash equilibria, finite improvement property, weakly acyclic, the property of being weakly acyclic, and so on. Okay. So this what I'll be talking today is mostly joint work with Christoph Abt, who's in CWI Amsterdam. Okay, so what is the subclass of game that we are interested in? So we are essentially interested in looking at these three properties. These are three important properties that we want to capture. First one is called the join the crowd property. So what does this say? This says that the payoff of each player weakly increases when more players choose the same strategy. Okay, so suppose I have chosen some strategy. Now if more players choose the same strategy, then they cannot decrease my payoff. Okay, this is one property. We'll see why this is natural. The second property is that the players may not have the same set of strategies. Okay, so these are allowed to be different. And the third property is you want to impose some kind of a neighborhood structure on this game. Okay, so think of this essentially as a coordination game with some neighborhood structure. So you're not trying to coordinate with all the players, but among some neighborhood of, you define a neighborhood and you're trying to essentially coordinate within that neighborhood. Okay. Now usually coordination games are defined in a way that the strategy sets are the same. Here that's not the case, so strategy sets are allowed to be different. So you have to essentially decide which coalition or which group you want to coordinate with. So that's the idea. Now why, so yeah, sorry.
What do you mean by this strategy? Are you talking about strategy types?
I will define it, but yeah.
Because supposing I follow something like tick for that something is different from for that for somebody else.
so let's say you take a coordination game. So each player has a set of strategies, right? What you normally assume, or the way you define it, is that set is the same for each player. And the one way of defining coordination game is you look at all the profiles where the choice is the same. That's going to be a Nash equilibrium. Okay, so I mean, it doesn't really matter, right? These are abstract choices. Label it with, I don't know, A, B, C, D, right? You take a profile where everything is A, that will be a Nash equilibrium. Okay. Okay, so why is this? There are various so there are various situations where you kind of end up in such a framework, and so one typical example is actually you think of mobile phone providers. You have a set of providers in pretty much every city. Now you want to decide which connection to take, right? So typically all these operators provide services like, okay, so if you call within the network, there is some, I don't know, so up to some n number of seconds or minutes, it's free, let's say. Okay, so all kinds of such offers might be there. Now it depends, so what you want to, the operator that you want to pick will actually depend on what you want to achieve, right? So if you have a lot of friends who are using the same network and then you talk a lot with them, then probably you want to take the same operator, okay? So in general, in any kind of networks where you have this notion of a product adoption, these kind of these characteristics make sense. Okay. So the model that we want to capture, it has a finite set of agents. You want to capture some kind of influence relation between these agents. Let's say we are talking about some kind of product adoption. So there's a finite set of product, there's a finite product set for each agent, and an agent can adopt a product from that set. So your strategies are essentially going to be these products. Okay, I'll define it formally in a moment. And usually it's assumed that there is some resistance level. So this is like you are in some situation, and if you want to change from that situation, there should be some incentive. Okay, so this is a normal assumption in these networks. I mean, it really depends on what kind of application you are looking at. So there is some stable state, let's say, and if you want to change from that, you need to have some incentive. So there is some threshold over which you need the influence, only then you want to change the state of the game. Okay, okay, so if these are the essential components that you want to model, then it looks like a natural structure to consider. These are weighted directed graphs, so you can consider a weighted directed graph. The nodes are the agents. The edges, these are directed edges. This captures the influence relation, and there's some kind of a quantitative value here. So these are weighted edges. So this essentially means that 1 is influenced by 3 and 4, and these values indicate the amount of influence. Okay, so 1 is influenced more by 3 than 4. Now, of course, these need not be, I mean, that's why it's directed. 1 being influenced by 3 does not mean that 3 is also influenced by 1. Okay, in general.
Okay. So they add up to 1. No.
Need not.
Yes. Yeah.
Sorry, excuse me.
Yeah.
So 1 is influenced by 2.
Yeah. No, 1 is influenced only by 3 and 4. 2 is influenced by 1.
Influenced by 1,
Yeah.
and 3 is influenced by 2.
Yeah.
So how 1 and 3 are influenced? Is there any relation?
No, it's not. No. Yeah. So it's just this graph structure. Okay. Okay. So now, so we associate with each agent, which is a node in this graph, a finite set. So I'm just using colors to represent this set. So these are intended to be products. Okay, some finite set of products. And we said there is a resistance in adopting a product. So we associate, these are called threshold values usually in the literature. So with each agent or each node, you also associate a number. These are called thresholds. Okay, so for instance here, the threshold for 1 is 0.3, the threshold for 2 is 0.4, and so on. Okay, so let me formally define this. Yeah. Yeah, I'll tell you. So I just, so these are the components that these components can be captured in a graph structure. Okay, so let me formally define what the model that we are looking at. So we are looking at a weighted directed graph. The set of vertices are the agents. This is a weighted edge relation, and the weights, let's say we normalize it, it comes from the interval 0, 1. Each, so there is a finite set of products. These are the entire products in the network. There is a function P which associates with each agent or each node in the graph some subset of products. Okay, so that agent is allowed to choose a product from that subset, from that set. Okay. Now there is also a threshold function which associates with each agent I a number between 0 and 1. So it's assumed to be strictly greater than 0. Okay. So this is the model. So let me just define two notations. Neighbor of a node I, these are the set of all nodes j in the graph such that there's an edge from j to I. Okay, so there's an influence. So I is influenced by j. That's the set of neighbors. I'm sorry?
What do the products consist of?
It's just a finite set. We don't care. So there is a finite set of products for the entire network. It's simply a finite set. Think of it, for the moment, think of it as a finite set. There is a function P which maps every vertex into some subset of these products. Okay. So with every vertex associates some set of products. The idea being that that agent can choose. It can be anything within this interval. So the weight can be anything in the interval 0, 1, and the thresholds can be any value. So if you want to, I don't care about. So this is the definition of the model. Okay. So I am not saying how the model is generated. This is the definition of a network. You give a graph, a weighted directed graph with these functions, that's your network.
Every edge has value, weight has the value between 0 and 1.
Yes.
It can be anything.
It can be anything. Yeah. Okay, so source nodes. Source nodes are all the nodes where all the agents which don't have neighbors. So these are nodes which are not influenced by any. So what is the interaction here? So how do you adopt a product? So I said, so each node is associated with a set of products, and the node wants to choose a product. So how does the node choose a product? Essentially, it wants to maximize the influence. Choose the product which maximizes the influence, right? So the interaction of adoption of product naturally defines a strategic form game. And what is this game? So each agent I can adopt a product from its product set Pi. Remember, P is a function from which associates with every agent a set of products. Okay, so each agent I can adopt a product from the set Pi or choose not to adopt any product. So this is T naught is simply a special symbol which says that the agent is not adopting any product. Okay, there are applications where you want this, there are applications where you don't want this. Okay, so it depends. So for instance, if you are trying to pick a school for a kid, of course T naught is not an option, right? If you are choosing a mobile phone operator, probably T naught is an option. Okay, so we'll just assume that T naught is there for this talk. Okay, so what is the game? The players are simply agents in the network. These are the nodes of the graph. The strategies is simply for player I is P of I, the set of products associated with I, or it can choose not to adopt any product, which is the special symbol T0. Payoff. So once you have a strategy profile S, so this strategy profile is again an n tuple where each component of that tuple will tell which product that player chooses. Okay. Once you have a strategy profile, what is the payoff of player I? If I is a source node of the network, what does it mean? I is not influenced by anyone, then it's simply 0 if the strategy is, if the node doesn't adopt any product, then it's simply 0. If it adopts some product in its product set, it's some positive constant C. Okay, essentially I is not influenced by anyone. If I is not a source node, so the I is influenced by some agents in the network, again, if the choice is T0, if the choice is T0, which means that he is not adopting any product, then the payoff is 0. Otherwise, so this is the interesting case. So you look at in the network, so we are looking at node I, which has some neighbors, right? You look at the choice that I has made, it's some product T, which is from his product set, okay? Now you look at all the neighbors who have chosen the same product T, you add up the weights. So that is this quantity here, you subtract the threshold, okay? So you simply add up the weights, subtract the threshold, that's the utility, okay?
Subtract the threshold, what is the significance? Okay, summing the weight is.
Yeah, so the idea behind threshold is that usually you don't want to change your state unless there is some incentive. So what is your resistance level? That's the idea behind threshold. There are cases when you want threshold, there are cases when you don't want threshold, right? So we are just looking at one case where you are looking at threshold. Of course, this threshold, the way I've stated it, it's very simple. It depends only on the agent, not on the product. Yeah, but you can also extend it to, to also depend on the product. So you can parameterize it with the product. None of the results change. It just gets more complicated. Okay. So it's the setting. Okay. Let's look at an example. This is a network. This is a valid network. So there are the agents are 1, 2, 6. The product set, it consists of 3 products, red, green and blue. The threshold for every player, let's say, is 0.3, so it's like a constant, okay? Suppose this is your strategy profile. What does that mean? It means that 1, 2 and 4 choose the color red. Red is in the product set for 1, 2 and 4, so they can choose. 3 and 6 choose blue and 5 choose green, okay? What is the payoff? The payoff for the source nodes, it's fixed, right? It's some constant C, okay? What is the payoff for player 1? The payoff of player 1, well, 1 chose red. There is precisely one neighbor of player 1 who has red, which is 4. The weight is 0.4, the threshold is 0.3, therefore the utility is 0.1. Okay, simple calculation. Is that clear? So you do the same thing for the other players. Okay, so this of course model of course satisfies the join the crowd property, which is that if a player chooses the same product that you've already chosen, then there's no way he can push down your utility, right? So it satisfies the join the crowd property, and this also defines a neighborhood structure on the set of players. So in game theory literature, this is often called graphical games. Okay. Now, so the first question. Okay, so these things we defined yesterday. What is a Nash equilibrium? It's a profile where no one wants to deviate. Okay, so this is the same definition that we had yesterday. So the first question is, so we already saw that in general strategic form games need not have Nash equilibria. Now we are looking at a subclass of strategic form games, clearly, because you have all these properties which are satisfied by this subclass. I mean, join the crowd, graphical game and so on, right? So you're looking at a subclass of strategic form games. First question is, does this subclass always have Nash equilibria? Yeah.
So I just wondered why is 0, 1?
There's no reason, it's just for simplicity, yeah. You can have whatever you want. Yeah. So nowhere do you have to add up to 1 or anything like that. Yeah. Okay, so this is the first question. Does the subclass always, you pick any game in the subclass, does it always have a pure strategy Nash equilibrium? Okay, and why is this question a bit interesting? Because of this property here actually. So if you think of congestion games, we said that congestion games are potential games. Okay, so congestion games, you're trying to minimize the cost, but there's the dual of congestion game, and it's called the fair cost sharing game, where you actually want more people using the same resource, because there you're going to divide the cost of the resource equally among all members. Okay, so those games are also potential games. So it's kind of, I mean, it's essentially a congestion game, but you rewrite. They have the join the crowd property, because you want more players to join the same, to use the same resource that you have chosen. It's these are potential games. So you might think that essentially you're doing coordination. Of course, coordination games have Nash equilibria, right? Here you're trying to do coordination. So it is, I mean, you might expect these games to always have Nash equilibria, but it turns out that this interaction between join the crowd property and graphical game makes it interesting. So the point is, now it's not clear which coalition you should join with, right? So you can end up switching, you can end up switching between correlations, and you might end up with no Nash equilibrium. Okay. So let's look at an example, and this is precisely the same network that we already saw. So this is the same network that we had two slides back. First observation is that the source nodes 4, 5 and 6, they have no incentive to choose T naught, right? Because if they choose T naught, you get 0, otherwise some positive constant. Okay, so we are only worried about what is the product chosen by these 3 nodes 1, 2 and 3. Okay. Okay, so each node in this cycle also have no incentive to choose T naught. Why is that? Because by just associating themselves with the source node that they are connected to, you can ensure a positive payoff, right? So T naught is not an option in this network at all. Okay. So let's look at some strategy. So let's say here, so this means that 1 chooses red, 2 chose red and 3 picks blue. Okay. So let's look at this profile. Is everyone happy in this profile? Okay, so let's look at this player 3. Is player 3 happy in this profile? Clearly he is happy because the other neighbor is 2, which has red, which has chosen red, but red is not in its product set, so he has no option. So 3 is happy. Okay. What about player 2? Player 2 has red and green in its product set, but red has more influence, incoming influence, so this is definitely the best response. Okay, that's also fine. Player 1, what is its best response? It should be blue because blue is in the product set and it has more influence, right? Player 1 is not happy in this profile. Okay, so let's pick player 1, ask him to change to his best response. So his best response is blue. When he changes to blue, then what happens? Player 2 suddenly becomes not happy because now he is getting negative payoff, right? So this is definitely not good. So let's say player 2 changes, he changes to green. Now player 3 is not happy because green is in the product set, and so this has more influence, right? So we'll pick player 3, make him switch to green. Now what happens? Now 1 is not happy because he is getting a negative payoff, right? So you keep doing this, you see that it ends up in what is called the best response cycle. Of course, this doesn't show that there is no Nash equilibria, but you just have to consider 2 more strategies which are not in the cycle, and you can convince yourself that there is no Nash equilibrium. Okay, so the idea here is, the problem here is that each node on this cycle is trying to coordinate with either the other node on the cycle or the source node, and it can't simply decide on where to coordinate. Okay. Okay, so then the next question you can ask is, okay, suppose, so Nash equilibria may not always exist, yes.
What about looking for the finite improvement property? Why look for Nash equilibrium?
Yeah, so I'll come to that. Yeah. So yeah, in general it won't hold because this is a counterexample, but are there classes where it holds? Yeah. Okay, so Nash equilibria may not always exist. So the next natural question is, suppose you are given a network S, is there an efficient procedure to check whether the network has a Nash equilibrium or not? Okay. Now this is also not easy. So this is NP complete. Of course, the fact that it is in NP is easy to see because you just guess a profile and check, right? Of course, you can check in polynomial time because you just have to run through each component. NP completeness. So let me try to give a short idea on this proof. So what you can do is reduce what is called the partition problem. So the problem is the following. You are given n positive rational numbers a1 to an, which adds up to 1. So it's normalized, it adds up to 1. Okay. Now the question is the following. So you have to pick a subset of these indices 1 to n such that you add up all the numbers where the index is in this set. That gives you half, which also means that you add up all the numbers which are not in this set, it gives you half, right, because the sum is 1. Okay, so this is the problem. Can you find such a set? That's the partition problem. So given an instance of the partition problem, which are these n numbers, you want to construct a network S such that there is a solution to this partition problem if and only if the network has a Nash equilibrium. Okay, so that's what you want to do. What we are going to do is take the same network which didn't have a Nash equilibrium, make 2 copies of it. Okay. Now the important point you have to notice here is that if you take this network, suppose for some reason you can make player 1 choose T0. Suppose you can make player 1 T0 a best response of player 1. Then of course this network has a Nash equilibrium, right? Is that clear? Because you just propagate it down, right? So if you can somehow make player 1, I mean T0 a best response for player 1, this network has a Nash equilibrium. Okay, so what we will try to do is construct a network in which if there is a solution to this partition problem, then player 1 choosing T0 would be a best response. Okay. So what you do is add n nodes. This corresponds to the indices 1 to n. They have in the product set of 4 and 4 prime. Okay. And then you add, no sorry, so not this node. I mean if you can force this node 4 to adopt T0, then you can ensure that this network has Nash equilibrium, right? Okay, so that's sufficient. Okay, so from the node that we have just added I1, which corresponds to this index 1, you add 2 edges to this node 4 and 4 prime. What are the weights? Is simply A1. Okay. From the second node, you add 2 edges to 4 and 4 prime. So is this network clear? Okay. And the threshold for 4 and 4 prime is simply half. So now you should be able to guess what is going to happen, because if there is a solution for the partition problem, what does it mean? There is a subset of indices which adds up to 1, right? The numbers add up to 1. Well, all those nodes, I mean these nodes correspond to those indices, all the indices which are in that set, you fix the strategy or the product red. All the nodes which are not in that set, you fix red prime. Okay. These weights will add up to will add up to half here. The weights here will add up to half. The payoff for adopting the product red is 0, right? Which means that T0 is also a best response, right? T0 also gives you 0. So therefore, this network will have a Nash equilibrium. Conversely, suppose the partition problem does not have a solution, then there is at least one part where the weight will be strictly more than half. That particular network will not have a Nash equilibrium because T0 is not a best response. Okay, so that's the idea. Now, of course, people in complexity theory will frown upon this reduction because partition problem has various problems, right? So it's known to be, I mean, there are pseudo polynomial algorithms for solving this. So you can give a reduction from 3CNF, except that the reduction is quite involved and you don't get any intuition out of it. Okay. Okay, so let's the point was that problem of deciding if there is a Nash equilibrium, it's not efficient. There is no efficient procedure. Yes.
What about the case where you don't have this nota, T0?
Then it's even worse. Yeah, actually, then it's even worse because the NP completeness continues to hold, but it holds even for I mean smaller subgraphs. Yeah. I will mention that towards the end. Yeah. Okay, so now if you look at this network here, you see that there are 3 source nodes and there are 3 different colors. Now, this is not a coincidence because of this theorem, which says that if you can pick a subset of the product set whose cardinality is at most 2. So, at most if you can pick a subset of products, at most 2 products in such a way that you can cover all the source nodes. Right, you take the intersection of that set with the product set of the source node. If that is empty, if that is non-empty, sorry, then this graph will always have a Nash equilibrium, and you can in fact compute the Nash equilibrium in polynomial time. Okay, so that implies that if the network has only 2 source nodes, it is guaranteed to have Nash equilibrium. If the network has only 2 products, it's guaranteed to have Nash equilibrium. Okay, so the fact that there are 3 source nodes and 3 different colors here, it's it is required. Okay, so in that sense, this example is kind of tight. So there are two other properties of this graph which immediately comes up. One is of course that it has source nodes, the other is it contains a cycle, right. So you can ask how important are these, right. So the first one is and the easiest is of course cycle. So the question that you want to ask is does Nash equilibrium always exist in networks where the underlying graph is acyclic and is free of source nodes, right. Acyclic should be very easy. Of course, it has Nash equilibrium. It has what is called a non-trivial Nash equilibrium. Non-trivial is that there is at least one agent or one node which chooses a product other than T naught. So everyone choosing T naught, if it's a Nash equilibrium, it's called a trivial Nash equilibrium. There's at least one agent which actually chooses a product. Okay, and this procedure is very simple. This is in game theory. It's called backward induction, and you just invert the graph because here you have a DAG. You invert the graph and do the same thing. Okay, so this you can take a look at it later. In fact, so you can show that this procedure characterizes all Nash equilibria. So this is like a non-deterministic procedure, but you take all the runs of this procedure. Those are the only Nash equilibria in this game. Okay, let's look at the other case. Graphs with no source nodes. What does this mean? This means that everyone has a neighbor. Okay, so everyone is influenced by some other agent. That's what it means. So this is an example of such a graph. First observation is the trivial profile is always a Nash equilibrium. If everyone chooses T naught, then of course no one has the incentive to deviate. The person who deviates get a negative payoff, right. So this is always a Nash equilibrium. So the real question that we want to ask is, are there non-trivial Nash equilibrium? When does that exist? Okay, and the answer is this. So there is a structural property of this graph which you can identify, and this is the property. It's called the self-sustaining subgraph. So a subgraph of your network, let's call it CT, is said to be self-sustaining for product T if it satisfies three properties. First is that the graph is strongly connected, the subgraph is strongly connected, and for every node in this subgraph, this product T is in the product set of that node. If you forget about all the nodes other than what you fixed by the subgraph, okay, and now suppose you assign this product to all the nodes in the subgraph, then none of the nodes here have a zero payoff, have a negative payoff, okay, in a way that says that this subgraph is kind of self-sustaining for that product, okay. So if everyone in this subgraph agrees to adopt the product T, then no one will get negative payoff. That's what it says, okay. And so for instance, this is an example for in this graph, these three nodes 1, 2 and 3, it's a self-sustaining subgraph for the product red, right, because if these three nodes adopt red, then you don't really care about the rest, they will never get negative payoff, okay. The theorem is the following. There is a non-trivial Nash equilibrium in your network if and only if there is a product T and a self-sustaining subgraph CT for that product. Okay, so you can find a non-trivial Nash equilibrium in this network if and only if you can find such a nice structure. Okay. Now this actually compute the non-trivial Nash equilibrium, except that it's not very efficient, right? Especially if your graph structure is something like a clique, then it's not going to be efficient. Okay, so the question is there a more efficient way of computing this non-trivial Nash equilibrium? Answer is yes, and it's a simple fixed point computation. So what do? You fix a product, let's say T. You start with this set, which is the set of all nodes which can possibly adopt the product T. Okay, set of all nodes where T is in the product set of that node. So this is like this big set. Okay, now you assign all these nodes the product T. Now some nodes are not going to be happy with this assignment because they might be getting negative payoff, right? What you do is you shrink this set by throwing away all these nodes which are getting negative payoff. Okay, that is what is being done here. You keep doing this procedure till the set shrinks and reaches a fixed point, what you can argue is that there is a non-trivial equilibrium if and only if there exists a product T such that at fixed point this set that you have computed is not empty. Okay. Is that clear? Is that statement clear? Okay. So, of course, this gives you a polynomial time procedure because once you fix a product, then this set xt can be computed in cube time, and then you are simply iterating over all products. Okay. So, you can, for such structures where there is no source node, you can check whether there is a Nash equilibrium, in fact a non-trivial Nash equilibrium efficiently in polynomial time. I'm sorry?
The Nash equilibrium depends on threshold as well.
It will, because your utility depends on the threshold. Yes.
But different thresholds you get different Nash.
Yes. Okay, so you can do this exercise and look at various complexity results, but let's get into what Jam was asking. So the question of finite improvement property. Okay. So finite improvement property, we already defined what it is in the previous class. So it says that you take this update dynamics, every improvement path is finite, so it terminates. Okay. Now you can ask whether these network games have the finite improvement property. Answer is of course no, because we saw a game with no Nash equilibria, right? Of course it won't have the finite improvement property, and this is simply the best response cycle. Okay, so this answer is no. So you can ask what are the substructures or what are the conditions that you should put on the network game such that you get a Nash equilibria, such that it has the finite improvement property. Okay. So this is simply the same thing that we defined yesterday. Do network games have finite improvement property? Well, the answer is very strange. Directed acyclic graphs, this you won't be surprised. It has finite improvement property because you are simply kind of propagating your product down. Even simple cycles do not have finite improvement property. Okay. So this is a bit disheartening because it's only simple. I mean, not even something like a simple cycle has this property. And why doesn't it have this property? Okay, so let's look at this example. It's a cycle with just 3 nodes, 2 products, red and blue. Let's look at this profile where 1 and 2 choose blue, 3 choose red. Is there a player who is not happy in this assignment? 2 is of course happy. Yeah. Essentially you want to follow your predecessor, right? That's the game. So 3 is not happy because he's getting a negative payoff. 1 is also not happy, right? Okay, so now let's say we let one switch, player 1 switch. Remember, in finite improvement property, let one player switch, okay, which is very important because if you have concurrent updates, then it may not terminate. Okay, so you pick a player you want to make him switch. So let's pick a player 1. What will he switch to? Red. So you get something like this. Now let's say you pick player 3, he will switch to blue, right? Now you have essentially just rotated the cycle, right? You keep doing this, you get a cycle. Is that clear? Okay, so even for simple cycles, you do not have finite improvement property. But does this game have a Nash equilibrium? Of course it has, right? Well, you start with this profile. Instead of scheduling 1, if you picked player 3, which is this, and asked him to play his best response, then everyone is on blue. That's of course a Nash equilibrium, right? So this is a game which is weakly acyclic. It does not have finite improvement property. Okay, so because there is an improvement path which converges to Nash equilibrium. Doesn't matter which profile you start with. Okay. Now, so the question that you want to ask is, so here it's very clear that the way you schedule players makes a lot of difference. Okay. So finite improvement property says it doesn't really matter how you schedule, it doesn't really matter how players update. You are always guaranteed to reach a Nash equilibrium. Weakly acyclic games say that you have to schedule in a particular way, you have to make sure that you update in a particular way, such that you in which case you reach a Nash equilibrium, right? So here it's a bit strange, so it's only the scheduling which matters. The way they update doesn't really matter because actually it's just a unique choice, right? But so the question that we want to ask is, can you schedule players in a way that all improvement paths are finite? Okay. So that's like in between finite improvement property and weakly acyclic games. Is that clear? So this we had already mentioned. So let's define what is a scheduler. A scheduler is simply, it takes as input a finite string of strategy profiles, and on the output it produces a player index. Okay, so it's simply a function f which takes on its input any finite string of strategy profiles. On the output it tells you which player which player has to be scheduled. Okay, some player index. So given any finite string of strategy profiles, the function f selects a player who did not select his best response in Sk. Okay. Now an improvement path, we say it respects a scheduler f if and only if you take any two adjacent strategy profiles in this path. By definition, we know that exactly one player changes. That's the definition of our improvement path. The player that changes is actually the player which was picked by this function f. Okay, if that holds, then you say that this improvement path respects the scheduler f. Is that clear? So what does potential games mean in this setting? It says for every scheduler, for all improvement paths in this game which conform to the scheduler, these are all finite. That's what potential games mean, right? What are weakly acyclic games? Well, you just change the quantifier. There exists a scheduler, there exists a improvement path which conforms to the scheduler, and that's going to be finite. That's what weakly acyclic game means. Okay. Now the question that we want to ask is there a scheduler f such that all improvement paths in this game which conform to f is finite? So it's like somewhere in between FIP and weakly acyclic games. Okay, is the question clear? Okay. So this, I mean, this has nothing to do with the network games that we started with, but one example of a game which has this property is what? The network game on the cycle, right? This respects that particular scheduler that we defined. Okay, so that's an example of such a game. Okay, so the picture that you have is you have games with finite improvement property, which is of course contained in the games with weakly in the weakly acyclic games, because every game with finite improvement property is of course a weakly acyclic game. And so this is the picture that you have, and for lack of imagination, let's call what we have just defined the class sched. Okay, so this contains FIP, because any game with FIP of course has a scheduler which terminates. This is contained in weakly acyclic games. Okay. Examples. So FIP we already saw. Congestion games, it's a large class of game which models many practical applications like road networks, packet switching networks, and so on. So these games have the finite improvement property. Weakly acyclic games, there are some internet routing games which fall into this class. So one important point about congestion games was there was this delay function. It only depended on the number of players using that particular resource. It didn't depend on the identity of the player. Okay. Now if you make your delay function dependent on the identity of the player, then you get what is called the congestion game with player specific payoffs. Now this class is no longer FIP, so these are not potential games, but you can still show that it has a Nash equilibrium by arguing that these class of games fall into weakly acyclic. Okay. So the natural question is, well, we have defined a new class here, sched, and what are the kind of games that you get here? We have seen one example, which is this network games on a cycle, but that's quite an artificial example. Of course, you can build, you can construct specific games which fall into this class, but is there any general class of games which fall into this class? Okay. Now, why is this useful looking at this class? There are various reasons. One is that you get, so you have this extremes. On one end you have FIP, on the other end you have weakly acyclic games. So it's useful to get a precise characterization of weakly acyclic games. So it could be that you don't really need all the, so weakly acyclic, remember, it's like a hand of God, right? You have to pick a player and tell him how to update, right? Maybe you don't need such a powerful scheduler, right? Okay, so it was shown that, I already mentioned that congestion games with player specific payoffs, they are not potential games, but they are weakly acyclic games. You can actually show that they fall into this class of sked. Okay, you don't really need the power of weakly acyclic. You can define a scheduler such that no matter how they update, you will converge onto a Nash equilibrium. Okay, so that is one result. There are some internet routing games which are in this class. So this definition is also useful to improve complexity bounds. So this is one example result. So there are certain games where, so FIP says, okay, every path terminates. Now what is the length of this path? The length of this path can be long. Okay. So there are certain games where an arbitrary path is guaranteed to converge in, let's say, some polynomial steps. But if you define a particular scheduler and look at the path which follows that scheduler, then that path might be actually much shorter. Okay. For this particular class of games, you can show that you can define a particular scheduler where the improvement path is at most order of log n, n log n. Okay, and it's also optimal. So this notion of scheduler, it's useful to precisely characterize where the game fits, whether you actually need this entire power of the hand of God, or you can also use it to look at the complexity of actually computing Nash equilibria. Look at the length of improvement paths. Okay. Yeah.
Checking existing scheduler is.
That can be difficult. Yeah. Yeah.
It's more about.
Yeah. So it's again, I mean, it's like defining potential function because there's no recipe for that. Yeah.
So is there some way of characterizing these schedulable games in terms of some kind of thing on potential function?
Yeah. That's a good question. So one thing that you can show is, well, the way I defined the scheduler, it was on finite prefixes, but you don't really need the prefix. You can just look, these are like memoryless strategies. So then you are essentially looking at some kind of a reachability game, and you can synthesize the scheduler as a winning strategy, which is positional. Okay. Okay, so yeah, so now, so we started the lecture yesterday by talking about dominance. So that's how we started. Then we looked at stability, then security. So these are the different kinds of solution concepts that we had in mind. Then we went on to finite improvement property and looked at weakly acyclic games. So the question was how can you converge to a Nash equilibria? Today we saw a specific subclass of games, and we asked pretty much the same questions: Nash equilibria, FIP, weakly acyclic, and so on. And now we are defining some kind of a scheduler, which again seems to have some use, but yeah, so you might ask why exactly are we doing all this? So let's go back to where we started, strict dominance. Okay. So this was our definition of strict dominance. A strategy SI is strictly dominated if there is some other strategy SI prime such that no matter what the other player plays, player I always gets better on playing SI prime, right? So this was the notion of strict dominance. Now let me generalize this a little bit, define a different notion which is slightly weaker. It's called never best response. So this says the following: a strategic game G, given a strategic game G, a strategy SI is a never best response if for all strategies of the other players, if there exists a strategy SI prime for player I such that SI prime gives you better. Okay, so what is the difference here? So here it says there is one uniform strategy. No matter what the other guys play, you get better, right? Here it says, well, the strategy which is giving you a better payoff can actually depend on the other guy's strategy, right? No matter what the other guys pick, there is some strategy which is better. That's what this says. Now, of course, if a strategy is strictly dominated, it is never best response, okay? So let's look at an example. This should make it clear. Look at this game. Look at this strategy C. Is C strictly dominated?
I hope it's visible.
C is not strictly dominated. Is it a never best response? So what does that mean? So let's look at it. So suppose player 2 plays X, okay? Does it make sense for player 1 to play C? No, because he should be playing A, right? Okay. Suppose player 2 plays Y. Does it make sense for player 1 to play C? Again, no, because he should be playing A. Suppose player 2 plays Z, then he should not play C, he should play B, right? This is the definition of never best response. So C is never a best response for player 1, okay? So if it's a never a best response, let's say we eliminate this strategy because we just agreed that player 1, no matter what the other player plays, should never play C, right? So let's just eliminate this strategy. Look at this subgame. Look at this subgame. Then Z is a never best response, right? Because if player A is playing, player 1 is playing A, then player 2 should play X. If player 1 is playing B, then he should play Y, right? So Z is a never best response. You keep doing this, you see that you have solved the game and you have reached this profile AX. Okay, so this is the same notion that we had, iterated elimination of some dominance relation, and the relation that we are looking here is never best response. Okay. Okay, so now let's complete the cycle. Again, I mean, you can show that, okay, this is an important point actually. So, iterated elimination of never best response, you can show that this is hereditary. So, this was the important property that we talked about yesterday. You can show that this relation is hereditary, which means that it's also order independent. So, the order in which you do this doesn't matter. The outcome is going to be the same. Okay. So, let's, and there are games that can be solved by iterated elimination of never best response. Which need not have the FIP. Yes.
So is there a relation between iterated never best response and being weakly or strictly dominated by mixing?
Yes. So it also captures the strict dominance by mixed strategies. So if a strategy is strictly dominated by a mixed strategy, then that strategy will also be a never best response.
But not the other way around, right? I mean, in your example, Z, right?
Yeah.
And the second step,
Yeah.
right? So it's because you have 0 and 2, right, for the best response for X and Y.
I don't think it works the other way around.
Right, it shouldn't, right?
Yeah.
But then you,
So essentially, it kind of captures elimination by strict elimination by mixed strategies. I mean, if something is strictly dominated by mixed strategy, then it also is never best response. Not the other way around.
and not even weakly dominated.
Weakly dominated, no. No, that's not true. Yeah. I mean, that's also why this is, this you can show is order independent, where weak dominance is not.
Right.
Okay. So why are we doing all this? So let's complete the cycle and this theorem. So if a game can be solved by iterating this process, then that game respects every fair scheduler. What does that mean? Well, so what does fair mean here? Fair just means that if a player is not happy, then eventually he becomes happy or he is scheduled. Okay, when he is scheduled, of course he becomes happy. Okay, so there is no infinite path where a player is unhappy and he is never scheduled. That's the notion of fairness here. Okay. So you can pick any scheduler which is fair, it's going to terminate under best response. So let me try and do a quick proof of this, at least I will give you some intuition. why this works. So let's define what is called a block. It's simply a finite sequence of strategy profiles. Okay. So suppose G can be solved by iterated elimination of never best response. Then by the order independence result, we know that the order in which you eliminate strategies doesn't matter, right? So we might as well assume that when we go from, let's say, G0 to G1, each time we make a step, we eliminate exactly one strategy. Okay, so let's assume that this is the sequence. The player index 1, 2 and all doesn't really matter, you just fix some sequence. Okay, so this means that when you go from G0 to G1, you are eliminating the strategy S1 of player 1. When you go from G1 to G2, you are eliminating strategy S2 of player 2 and so on. Okay, it's some sequence. Now, let F be any fair scheduler and rho be a best response improvement path which respects the scheduler F. What you want to argue is that this improvement path is finite, correct? That's what you want to argue. Okay. So now rho can be broken up into these blocks. So what are these blocks? These are blocks in which you take any player who is not playing, who is not happy at the first state. Okay, so this is a sequence of strategy profiles. You take any player who is not happy in the first strategy profile, eventually he is scheduled within this sequence. That's the definition of a block. Okay. So you can always rewrite this improvement path as a sequence of sequences of such blocks. Is that clear? Now what do you do? So you have a iterated elimination of never best response sequence. You have this improvement path rho which is split up into these blocks. What you want to argue is this path is finite. Okay, now let's consider the first block. It's some finite sequence of strategies. In this iteration, when you go from G0 to G1, we said that the strategy S1 of player 1 is getting removed. Okay, so there are two cases. The first case, suppose this strategy S1 was actually being used by player 1 in S0. What does that mean? Of course, player 1 is not happy, right? It doesn't really matter what the other players are doing. He will never become happy because it's a never best response, correct? So this strategy is a never best response. So no matter what the other players do, he'll never become happy, right? What does that mean? Well, it means that in this block, he is going to get scheduled once. When he gets scheduled, he chooses his best response, right? So he changes from this S1 to some other strategy. Now, since S1 is a never best response, he will never switch back to S1, correct? Because you are looking at best response improvement paths. Okay, so that is one case. The second case is when player 1 is not using S1, it's using something else. Again, by the same argument, you can say that because S1 is not a best response, the player 1 will never switch back to S1. Yeah.
How many blocks can belong to strategies?
It's the other way around, right? A block is a sequence of strategy profiles. Yeah, it's a finite sequence of strategy profiles. Okay, so anyway, the summary is that strategy S1 will never appear in this suffix B1, B2 and so on. So you've looked at B0, so this was your improvement path. We have looked at B0 and we have argued that the strategy S1 will never appear in B1, B2 and so on. What does that mean? Well, this suffix, this improvement path, the suffix of this improvement path essentially is in the subgame G1, right? That's what it means. You keep doing this, you take the next strategy which is eliminated, do the same reasoning. Then you see that the suffix B2 and so on will be in the subgame G2. You keep doing this. What does it mean to say iterated elimination of never best response? You solve the game. Well, it means that GM has precisely one strategy profile, right? Which means that this path has to be finite. Okay, so this is a general class of games. So you take any game which can be solved by iterated elimination of never best response, that falls into the class KID. Why? You just do round robin scheduling. You just don't care, right? It's a fair scheduler. Okay. So we had also mentioned that concurrent updates. So this is a problem for FIP because even if a game has the finite improvement property, it may not converge with concurrent updates. But if a game can be solved by IENBR, then you don't really care. So you can allow players to update concurrently. Why is that you don't really care? Because all the strategies which are being thrown out are going to be never best response, right? So what is the maximal concurrent scheduler? You pick all the players who are not happy and let them update at the same time. This is going to converge, okay? So this, so let me stop with this. So we started this exercise with an introduction to game theory. We were looking at the three main types of solution concepts: dominance, stability, and security. Then we asked the question, okay, how do you actually reach a stable outcome? Well, you can follow improvement paths and reach a stable outcome. We looked at a subclass of games and pretty much asked the same questions: when does it have Nash equilibria, and looked at some complexity results. And we saw that it's useful to look at this fine-grained analysis of having a scheduler which kind of distinguishes between FIP and weakly acyclic games. What are natural classes of games which fall into this category? Well, you take any game which can be solved by never best response. That's an example for you. So essentially, it's kind of closing the gap, closing the cycle between these notions of improvement paths and the notion of dominance, and we are essentially using a notion of scheduler and fair scheduling, which is very common in distributed computing. Okay, so yeah, that's it. I'll stop here. Thank you. Questions?
This goes only one way, right?
It goes only one way. Yeah.
So your class of schedulable games may have more.
Yes, yes. And it's definitely, IENBR is definitely not a characterization. Yeah.
And also for these admissible strategies,
Yeah.
in general, even if it's not solving the game,
Yeah. Yeah.
even if you have some outcomes,
Yeah.
is there some characterization, other potential games or something?
Not that I know of, no. So admissibility, it's a bit, I mean, people don't even agree on the definition of rationalizable strategies, because the question is when you go from a game, when you go from a game to a sub game, it should be rationalizable in which game. So each person has his own definition. Some people take it to be rationalizable in the first game, some on the second game. There are some conditions under which it doesn't really matter, but I don't know of any corresponding result there. Yeah.
I mean, with what the definition?
Yeah.
I'd be more interested in the characterization of what is left over.
Yeah. So I don't know. Yeah. Yes.
So yesterday you mentioned that strict dominance can be characterized with rationality and common rationality. Do you have something like that for this?
Of course, I mean, strict dominance is kind of subsumed here.
Yeah, but so do you have an equivalent characterization?
No. So there is no characterization. Yeah. So it's again a one-way kind of result. So there is no characterization. Yeah.
Yeah, but in terms of the investment principle,
Yeah, that's what I mean.
I mean, you know, characterization of potential games is something that.
Yeah.
But if you were asking, is there some common value, common knowledge kind of notion? But rationalizability, I think, you know, particularly has been doing kind of work precisely on that. But there are no definite answer. It's not like Auman's theory.
Yeah. Yeah.
But at least for some specific things, there is some. You can give it as a kind of fixed point of an argument. Some evolution. As neat as.
Yeah. Yeah.
So like, I don't believe that no one choose never been responsible.
Yeah.
It's more common.
Right, that's what I would think.
That's why I said there are a lot of these controversies.
Right.
But certainly, I think the rationalizers seem a good
Candidate for
good candidate.
Okay, thank you.
Thank you.